Earth, the only planet we know of that can sustain life, does so not just because of its liquid water or oxygen-rich atmosphere. A less discussed but vital element is the magnetic field that surrounds the planet. Earth's magnetic field acts as an invisible shield, protecting the surface from the relentless onslaught of charged particles from the sun and deep space. But what would happen if that protective layer disappeared? The loss of the magnetic field would not happen in a single moment, but the consequences could spread and escalate rapidly. From uncontrolled solar radiation to atmospheric loss, biological disruption, and even complete ecosystem change, each event would have unpredictable ripple effects. To understand this scenario, we need to start at the core: what Earth's magnetic field is, how it forms, and why it matters. Part 1. What is the Earth's magnetic field, mechanism, and core role? The Earth's magnetic field, or magnetosphere, is a giant electromagnetic field surrounding our planet, created by the movement of liquid iron in the Earth's outer core. This process, called geodynamo, is a combination of factors. Liquid outer core contains mainly iron and nickel in a molten state, has high electrical conductivity. The rotation of the Earth creates convection currents and eddy currents, Coriolis effect, forming spiral currents. Induced currents generate magnetic fields through Faraday's law, thereby forming magnetic fields. The magnetic field is not fixed, but constantly changes in intensity, direction, and shape. Currently, the magnetic field is weakening and showing signs of polar shift, recorded in global geomagnetic surveys. Structure of the magnetosphere. The Earth's magnetosphere is shaped like a water drop flattened by the solar wind. The bow shock, the first layer exposed to the solar wind, where the plasma is deflected. The magnetosphere, the region surrounding the Earth affected by the magnetic field, extending hundreds of thousands of kilometers to the tail. The ionosphere and the Van Allen belt contain highly charged particles, protecting the Earth from cosmic radiation. The existence of the magnetosphere helps retain the atmosphere, block cosmic radiation, and direct the flow of high-energy particles from the Sun. The key role of the Earth's magnetic field. The magnetic field is the most important biological shield of our planet. Without it, life as it exists today would be difficult to exist. The role of the magnetic field includes: A. Protection from the solar wind. Without a magnetic field, solar wind would deplete the atmosphere over time, as has happened to Mars. B. Reducing ionizing radiation. Magnetic fields help to direct and scatter cosmic radiation and solar flares away from the Earth's surface. C. Maintaining a stable climate. Loss of magnetic field would allow light gases to escape, altering atmospheric composition and global climate. D. Biological navigation. Many species use the magnetic field to navigate. Loss would disrupt migration and foraging behavior. Warning signs of a weakening magnetic field. Data from satellites, such as Swarm ESA and geomagnetic monitoring stations, show that the strength of the Earth's magnetic field has decreased by about 10% over the past 200 years. The South Atlantic Anomaly region has an unusually weak magnetic field. Magnetic north is rapidly moving towards Siberia. These signs suggest that a geomagnetic reversal may be taking place. In which magnetic north and south will switch. This process occurs on average every 200,000 to 300,000 years, but the last time was over 780,000 years ago, suggesting we may be on the cusp. Earth's magnetic field compared to other planets. To understand the importance of the magnetic field, we can compare it with the neighboring planets. Mars. There is evidence that it once had a strong magnetic field, but it later lost it, then lost its atmosphere, turning into a barren planet. Venus. No magnetic field due to slow rotating core, thus thick carbon dioxide atmosphere, extremely strong greenhouse effect, surface temperature above 450 degrees Celsius. Jupiter has a magnetic field 20,000 times stronger than Earth's, protecting its satellite system from intense solar radiation. The Earth's magnetic field is a vital biophysical structure that protects life from harmful cosmic agents. The loss of the magnetic field would not be a mere physical change, but an event that could lead to mass extinctions, severe climate change, and redefine the entire evolutionary mechanism of life on Earth. Part 2. Immediate consequences. Earth is no longer a magnetic fortress. When the Earth's magnetic field disappears, whether gradually or suddenly, the physical and biological effects will appear almost immediately. To understand the consequences, it is necessary to separate the effects by space layer, from the atmosphere, ionosphere, stratosphere, to the planet's surface. 1. The heavenly gate opens wide. Cosmic radiation floods in. Earth's current magnetic field acts as a powerful filter, blocking most of the solar wind, a stream of charged particles consisting of protons, electrons, and heavy ions that emanates from the sun's corona. Without the magnetic field, this shield disappears, and these streams of particles would collide directly with the ionosphere and stratosphere of the atmosphere. The average solar wind speed is about 1 to 3 million kilometers per hour, and it contains enormous kinetic energy. Without the guiding magnetic field, high-energy particles interact directly with the atmosphere, creating extremely strong ionizing radiation, destabilizing the ionosphere and interfering with all long-range radio waves. Increased formation of highly reactive molecules, such as NOx, nitrogen oxides, which rapidly destroy the ozone layer. Large-scale electrical charges in the atmosphere, leading to unusual electrical discharges similar to lightning, even under normal conditions. 2. Ozone depletion, a gateway to ultraviolet. When the solar wind hits the upper atmosphere, without being deflected by the magnetic field, the ozone layer will be destroyed faster than it can be regenerated. The ozone layer, which filters out ultraviolet radiation UVB, UVC, will thin or disappear in many areas. Increased UVB radiation into the Earth's surface. This type of radiation can cause skin cancer, cataracts, immune system failure, and DNA mutations. Photosynthesis is severely affected. Plant cells are very sensitive to UV, leading to reduced photosynthetic capacity, affecting the entire food chain. Phytoplankton in the ocean, which is the foundation of marine biology, will collapse, affecting all marine life. 3. Increased terrestrial radiation. The planet's surface becomes dangerous. Without a protective magnetic field, the Earth would no longer be a safe environment for life as we know it. The amount of ionizing radiation at the ground would increase many times over. This is the type of radiation that can penetrate the human body, break down DNA structure, and increase the risk of cancer. The rate of genetic mutations in the genomes of animals and plants would increase significantly, accelerating the evolutionary process, but also increasing the number of deformities and the possibility of extinction. Effects on technology. Electronic devices, from phones, satellites, power grids, GPS, would operate unstable or completely fail due to high radiation and loss of magnetic orientation. 4. Consequences on animals and biological orientation. Many animals, especially migratory birds, sea turtles, salmon, use the Earth's magnetic field as a natural compass for orientation. When the magnetic field disappears, they lose their ability to determine direction, leading to lost migration routes, failure to find places to lay eggs, and the decline in population. Some species may become extinct, especially if they reproduce on long migration cycles. Subterranean animals, mole rats, ants, and insects, such as bees, are also severely affected, as many species use internal magnetic sensors to navigate. 5. Could Earth lose its atmosphere? A major concern is atmospheric stripping, which occurs when there is no longer a protective magnetic field. A typical case is Mars, which once had a thick atmosphere, liquid water, and a magnetic field. As the core of Mars cooled and the magnetic field disappeared, the solar wind slowly stripped away the atmosphere, leaving the planet dry and uninhabitable. Although Earth has greater gravity than Mars, which makes it better at holding on to its atmosphere. If the loss of the magnetic field continues for thousands of years, the lighter gases like hydrogen and helium will gradually be pushed out into space. Over time, this could lead to a loss of atmospheric pressure enough to support liquid water and life. The loss of Earth's magnetic field would have a series of immediate consequences, spreading from the atmosphere to the ground and the entire biosphere. This is not just an astronomical or geological problem, it is a global biological and environmental crisis. The consequences go beyond immediate disruption. In Part 3, we will delve into the long-term changes to the climate, atmosphere, and the impact on the viability of life on Earth for thousands of years to come. Part 3. Long-term consequences, when the Earth becomes uninhabitable. After the Earth's magnetic field disappears, in addition to the immediate consequences analyzed in the previous section, radiation, biological mutations, loss of orientation, the long-term changes will really determine the future survival of the planet. We will analyze in depth three main axes: climate, atmosphere, and the ability to sustain life on a millennium scale. 1. Global climate fluctuations. The Earth's magnetic field is not only a shield, but also a channel shaping the flow of energy to and from the planet. When it disappears, cosmic radiation and solar rays are no longer evenly dispersed, but are concentrated in weak magnetic regions, typically the mid-latitudes, leading to global temperature extremes. Some regions become super hot due to direct absorption of radiation, while other regions are suddenly cooled by the shadow of the turbulent atmosphere. The disappearance of upper-level jet streams, causing weather instability, no longer having the current seasonal rotation. Redefining global weather. The solar wind interacting directly with the ionosphere will create large-scale induced currents, thereby directly affecting the evaporation-condensation cycle in the atmosphere. Electromagnetic storms can become a new type of weather, with plasma currents appearing in the lower atmosphere, creating unusual electrical noise rains, threatening both equipment and living things. Climate poles flip. Without a magnetic curtain to regulate the flow of radiation, new magnetic poles may temporarily form in different regions. For example, the equator may become colder due to loss of uniform absorption. As a result, the tropics will no longer be warm all year round, while temperate regions will become more extreme, upsetting the entire biosphere and agriculture. 2. Atmospheric erosion, the path to extinction. After the disappearance of the magnetic field, the atmosphere became the only shield between Earth and space. But this layer is not stable without the protection of the magnetic field. A. Atmospheric escape. The solar wind will gradually pull light elements, such as hydrogen and helium, out of the outer atmosphere, exosphere, similar to the process that happened to Mars. This effect is slow but inevitable. Over several thousand to several million years, the atmospheric pressure will decrease sharply, leading to water cannot exist in liquid form. Temperature imbalance between day and night, super hot days, super cold nights. Carbon dioxide and methane emissions are not enough to retain heat. The greenhouse effect weakens, the Earth gradually cools. B. Atmospheric composition changes. As UV and cosmic rays break apart molecules, the ozone layer is severely damaged, leading to increased concentrations of nitrogen dioxide, low-level ozone, and highly reactive compounds, turning the atmosphere into a toxic mess. Without the photosynthesis respiration balance between plants and animals, the atmospheric ecosystem becomes abiotic. 3. Life pushed to its limits. A planet without a magnetic field is hostile to DNA-based life, and Earth will be no exception. A. Disruptive genetics. Cosmic rays and ionizing radiation break DNA strands, leading to massive mutations. Not in an evolutionary way, but in a biologically unstable way. Rates of cancer, infertility, and genetic diseases increase exponentially, especially in mammals. The biological retreat. Many species will retreat to caves, deep soils, or the seafloor, where there is a better physical shield against radiation. Bioluminescent, heterotrophic, or chemotrophic organisms in volcanic vents, deep-sea black holes, etc., will replace surface life. Gradually, the Earth will return to its Precambrian state, with few complex organisms, mostly single-celled or anaerobic. C. Second-level extinction scenario. Unlike asteroid impacts or supervolcanic explosions, where the biosphere has a chance to recover, the loss of the magnetic field is an irreversible process if the Earth's core has cooled or lost its relative rotation. In this scenario, the Earth does not reset, but rather enters a biologically dead phase. If life survives, it will be completely alien species, able to survive on ionization, plasma, or energy from currently unknown sources. When Earth loses its magnetic field, it's not just a shield that's gone. It's the beginning of a planetary biological retreat. The climate goes haywire, the atmosphere is eaten away from the outside, and life, as we know it, slowly disappears from the surface. In Part 4, we'll go further. If humans survive, how will they survive? Is technology enough to fight the universe when nature gives up its role as protector? Part 4. Humans versus space, technology to replace nature. When the Earth's magnetic field collapses, the consequences are clear. Radiation floods the atmosphere, the climate is disrupted, and life is lost. But a bigger question arises. If humans were still around today, would technology be enough to replace nature and sustain life? The Earth's magnetic field is generated by the movement of the liquid metal core. When it disappears, humans can build a satellite system to create an artificial magnetic field, similar to the idea proposed by NASA for Mars. Humans can place a powerful magnetic field generator at the Lagrange point between the Earth and the Sun to deflect the solar wind. Build a low Earth orbit, LEO radiation shield, a giant electromagnetic shield, creating an artificial protective layer around the planet's surface. Difficulties. Requires huge energy. The system is vulnerable to damage due to unshielded radiation, and must be maintained continuously without interruption. No magnetic field. Ozone layer is broken down. Ultraviolet and ionizing radiation separates gas molecules. City-scale atmospheric filtration GeoBubble. Create local protective domes that can filter UV. Regenerate oxygen using microalgae or solar water splitting technology. Create artificial microatmosphere. Use inert gases, such as argon, to reduce ionization reactions. Partially replace the living environment. Although feasible in a closed environment, this method cannot be applied to the entire planet, only suitable for city bubble survival oases. As the Earth's surface becomes toxic, humans are forced to move into underground or oceanic settlements, protected by layers of soil, water, and metals that can block radiation, or gradually move the population to space stations, orbital factories, where local magnetic fields can be built and the environment can be adjusted as desired. The ability to survive will no longer depend on the mother planet, but on an artificial closed ecosystem. Humans can prolong life after the Earth loses its magnetic field, but only within a local, limited range, and completely dependent on technology. Existence is no longer living with nature, but resisting the universe. In Part 5, we will analyze: if the loss of the magnetic field is inevitable, is there any way to predict and prepare before it happens? Part 5. Warning signs. Can we prepare? The possibility of Earth losing its magnetic field is no longer a science fiction scenario, but a geophysical possibility that could happen. To understand whether humanity can prepare, we need to delve into the actual manifestations that have occurred and are occurring, as well as the ability to predict this event. The Earth's magnetic field is decreasing. According to measurements from satellites, such as Swarm ESA, over the past 200 years, the Earth's magnetic field has decreased by about 9%. One of the areas with the most significant decrease is the South Atlantic region, known as the South Atlantic Anomaly, SAA. This is where the magnetosphere is so low that solar radiation can easily penetrate the lower atmosphere and affect satellites operating there. While the decrease in strength does not mean a complete loss, it does indicate instability in the outer core, where the magnetic field is generated by the convection of liquid iron. The appearance of localized weak areas could be the beginning of larger changes in the structure of the magnetosphere. Earth's magnetic field is not fixed. In the past, there have been pole reversals, north to south, south to north, called geomagnetic reversals. Evidence of these events is preserved in basalt layers, ocean floor sediments, and magnetic crystals. On average, a reversal occurs every 200,000 to 300,000 years. The most recent reversal, called the Lachamp event, occurred about 42,000 years ago and lasted for several hundred years. During that time, the magnetic field weakened to 5% of its current strength, leading to increased cosmic radiation and climate change. Currently, the North Magnetic Pole is moving rapidly, approximately 50 to 60 kilometers per year, an unusually high rate. A reversal does not mean a permanent loss of the magnetic field, but the reversal process can lead to periods of very weak magnetosphere, from several decades to several thousand years, with consequences similar to a temporary loss of magnetic field. Currently, scientists use magnetohydrogenic (MHD) models to simulate activities in the Earth's outer core. Thanks to supercomputers and data from global geomagnetic stations, we have the ability to detect unusual trends, but predicting exactly when the pole will reverse or lose its magnetic field is still not possible. A major challenge is that the magnetic cycle is nonlinear, depending on many geological variables inside the Earth that we cannot measure directly. This makes the prediction models still approximate. What can be done now? Continuously monitor the global magnetic field, especially in regions like the SAA. Strengthen shielding for satellites operating in low orbit, an area vulnerable to radiation if the magnetic field weakens. Develop artificial magnetic field technology, not only for space missions, but also for future prevention if needed to protect populated areas. In short, signs of magnetic field weakening are present, but the timing of complete loss remains a mystery. Humans can monitor, predict to some extent and build contingency plans, but to fully confront a magnetically demagnetized Earth, a major leap in understanding the planet's core and global-scale defense technology is needed. Part 6. Exiting Earth Scenarios. When the planet is no longer safe. If the Earth loses its magnetic field and humans cannot adapt to the high radiation environment, life will be pushed into a risky survival phase. In the worst case, when the magnetosphere disappears completely for thousands of years, the scenario of migrating from Earth to ensure the survival of humanity has become an unthinkable but necessary option. The following analysis will focus on the feasibility of leaving the planet from the perspective of modern science and technology. 1. Motivation for leaving the planet. When the magnetosphere is gone, the consequences do not stop at increased radiation. Atmospheric erosion will reduce air density, increasing mortality due to lack of oxygen. Genetic mutations will spread in plants, animals and humans, reducing the quality of life and fertility. Radiation affects agriculture, crops die en masse, food chains collapse. If artificial magnetic shield technology is not yet developed enough, then finding and moving to a place with similar conditions to Earth that can be improved is a strategic move. 2. Potential destinations. A. Mars is the most promising candidate at present. However, Mars has no magnetosphere, and its atmosphere is extremely thin, only about 1% of Earth's atmospheric pressure. Build underground cities to avoid radiation. Use artificial magnetic domes or anti-radiation materials, such as regolith, for shielding. B. Moon. Difficult to be a permanent settlement due to the lack of atmosphere and stable water source, but suitable as a transit station for longer journeys. C. Europa, Titan, moons of Jupiter and Saturn. Contain water ice and signs of underground seas, but reaching and building an ecosystem here requires extremely advanced cold mining technology, which cannot be realized in the next 50 years. 3. Necessary technology. Multi-generation spacecraft. If moving outside the solar system, because there is no place with the conditions, it is necessary to design a spacecraft that can live for generations, recycling water, food and air. Bioengineering and genetics. Modifying the human body to resist radiation, like researching the tardigrade or Dinococcus radiodurans genes, super hardy creatures. Small nuclear technology or fusion reactors, providing stable energy for interplanetary migration. 4. Current limitations. Huge cost. The cost of putting 1 kilogram of material into orbit alone is currently more than $2,000, not including the interplanetary distance. Travel time. Reaching Mars takes 6 to 9 months. Reaching Proxima b, the nearest planet outside the solar system, would take thousands of years with current technology. Social psychology, limited life, cramped spaces, prolonged isolation are major barriers that have yet to be solved. Conclusion. With the Earth's magnetic field gone, space migration is a last resort, not an ideal solution. Long-term survival beyond the planet requires major breakthroughs in biology, energy, and space transportation. Currently, natural magnetosphere protection and the development of artificial shielding technology remain more realistic paths than leaving the planet. Part 7. Conclusion. Could a magnetic field-free Earth exist? When we put together all the implications of the loss of the Earth's magnetic field, one thing becomes clear. The magnetic field is not just a physical phenomenon, but a pillar that protects life. From the ionosphere to the biosphere, from animal orientation to biological protection from radiation, the magnetic field acts as an invisible shield that keeps human ecosystems and technologies functioning properly. If the magnetic field disappears, the Earth will not immediately become dead, but it will enter a long-term process of environmental degradation with the following consequences. Increased exposure to cosmic radiation causes genetic mutations, weakened immune systems, increased risk of cancer, affecting both humans and animals and plants. Atmospheric changes. The erosion of the atmosphere by the solar wind will gradually thin the atmosphere, reducing its ability to retain heat and protect biology. Ecosystem changes. Magnetosensory animals would be disoriented, food chains would be disrupted, and ecosystems would be disrupted. Impact on modern technology. Satellites, power grids, navigation, and communications would have to be redesigned to withstand the effects of radiation and induced currents from the solar wind. However, humans are a highly technologically adaptable species. In a world without magnetic fields, artificial alternatives would become essential. The ultimate question is not just can Earth survive, but can life adapt when the magnetic field disappears? The answer is yes, but at great cost. In such a scenario, humans will need not only a deep understanding of geophysics, but also a fusion of technology, biology, and the environment to survive in a world without its invisible shield, a world that is colder, more dangerous, and more unstable than we have ever known.
And that's what it would look like if Earth lost its magnetic field. Thanks for watching until the end. If you found this content interesting, don't forget to like, subscribe, and turn on the notification bell so you don't miss the next What If series, bizarre but thoughtful scientific hypothetical scenarios. Are there any topics you'd like to explore? Feel free to leave a comment. I read them all. See you in the next video.